Next, DJ Snyder with iCore. Where are you at, DJ? There you are. Are you ready to go?
Right here, ready to go. Can you hear me?
Okay. Yep.
Okay.
So DJ is a 2009 grad from Tech.
Okay, how's that?
Good.
Cool. Hey, so today I want to talk about downhole separation, gas and solids. My background was completions and came into production a few years ago. When I started getting into production, it was something I'd always heard about, but it was never really like nobody ever dove too deep into it. Come to find out, it was maybe a little bit misunderstood of a topic. So really, I just wanted to bring it back to the basics. And so there's been a lot of research done on it from the 1930s, 40s, 50s, and then kind of updated for some horizontals. So again, just kind of back to the basics. I think it's always been an issue, and it will be moving forward. But again, want to talk about production lift types, a lot of the unconventional lift types, gas separation background, kind of what's been done, what have people looked at, and then what we're looking at now. The different type of downhole gas separators. So there's a few. We'll just kind of dip into the basic gas separators, talk about gas separation capacities, because that's something that service companies always talk about is gas separation capacities. But where do those capacities come from? How do you calculate those? And then some research we did last year when work started to slow down during COVID, we started focusing on solid separation and combining that with CFD, computational fluid dynamics. And then just kind of a general discussion. So artificial lift methods in the US, there's a few more beyond this, but electronic submersible pump, ESPs, rod pump, gas lift, plunger lift, and jet pump. So a rod pump is basically, we've seen it, a pumping unit. That pumping unit is tied to a rod string. That rod string runs downhole to a subsurface pump. It reciprocates up and down. The majority of US wells today eventually go to some type of a rod pump well. The next is, and so each one of these rod pumped wells has a gas separator. So downhole pumps don't like gas. Gas is fairly compressible, whereas a fluid is not compressible. So its efficiency, the whole system loses efficiency if gas is in that system. Same thing with an ESP. So an ESP is an electronic submersible pump. So it's a series of motors that spin a pump, and on those they have gas separators as well. So they're used in a higher volume type well. A gas lifted well, you're essentially pumping gas down the annulus and injecting it into multiple gas lift valves and trying to reduce the hydrostatic column so the well will lift. Plunger lift can be combined with gas lift, where you have basically a tool that travels up and down in that tubing and helps lift some of that fluid so that gas can flow. And then jet pump is something that is still used today, but not quite as much. So today, again, we're talking about rod pump, gas separation, solid separation, and a lot of these gas separators can be tied to ESPs as well. So again, just taking back to basics, separator capacities, and looking at the rod pump system as a whole system. So what is it? What are its components? So it's a motor. It's an electric motor. It's fairly efficient. It drives gears. The gears on the pumping unit are relatively efficient as well. The rod string tied from the surface to downhole runs through tubing. That tubing rubs on tubing, so that's a little bit less efficient. The downhole pump is fairly efficient, so when it goes up and down, it pulls fluid with it, and that's efficient as well. And then we get to the downhole gas separator, and so that was the thing that varied the most, from 0 to 99%. So you can have a well that's gas locked, that's pulling in gas and essentially cannot pump, or you can have a very good gas separator that pulls in 100% fluid, and the whole system is more efficient. So overall, we wanted to look at the downhole gas separator and how it affects the whole system. So again, gas separators have been around for a long time, and the thing that's changed in the last few years is horizontal well bores. So historically, we've been able to sump a pump down below our perforations, and so gravity essentially does all the work. As fluid falls down, because gas is lighter than fluid, gas will go up. So slowly the liquid will come into the well bore and gas will rise, will produce gas up the annulus and the fluid through the tubing. So again, up until the early 2000s, we were able to drill a little extra rat hole, sump a pump down below the perforations on our target zone, and then put a pump below that target zone. Whereas today, drilling horizontal wells, we're either stuck leaving a pump at kickoff point or somewhere in the curve. With these rod pumps and these ESPs, they don't like to go through bends. So it's a moving components, and if we put them through a curve, they typically wear out. So we'd see more failures, and essentially today we see a lot of pumps stuck at kickoff point or sometimes pushed down through the curve. So we're now having to produce fluid and gas around that pump, and that's why a gas separator is a lot more necessary today than it may have been in the past. So to look at just a conventional gas separator from the top to the bottom, is we stick our pump at the top inside of the tubing. We have just a conventional collar, a perforated sub. Within that perforated sub, we have what we're calling a dip tube, which is essentially just a smaller tube, another collar, and then some joints below it. So fluid will be produced up by that gas separator, and then some fluid will come into the separator in between that perforated sub and dip tube, and up that dip tube to the surface produced through the pump. And then the gas will go up the annulus. But if we produce too much, we'll pull in some of that gas in with that fluid. So there's been some pretty good case studies, laboratory studies about injecting gas and fluid. So this study was done with water and air. So take all of this as not solid science, but essentially case studies, rules of thumb, and every application is going to be different. So the picture on the top left is the dip tube. The inside is the dip tube, the outer is the outer housing. So we're essentially mimicking a downhole gas separator. We're injecting gas and producing fluid through that inner dip tube. So we're pulling fluid down at a constant rate of 5 inches per second, or equivalent to 243 barrels a day, while injecting gas. And so that gas is able to rise faster than we're able to pull it downward. And so at 6 inches per second, or 275 barrels a day, that gas we can now see is almost at that dip tube intake. So as soon as that gas comes into that intake, our pump is going to be less efficient. So at 9 inches per second, we're pulling down that fluid really fast. We're at 420 barrels a day, and we're pulling in a lot more gas. So the pump is much less efficient. And so this is the basics of bubble rise velocity is something we'll talk about, or just fluid production, and then the gas separation area. All of those things are important to understand. So from that study, we're able to determine that, again, gas is lighter than liquid, so gas will rise. Gas will rise at a certain rate as fluid is being pulled down. So we can do volumetrics and calculate the amount of fluid that we can produce per square inch. So in this case study with water and air, we're able to produce 50 barrels of fluid air-free per square inch. Okay. So now we're looking at the surface area and the surface area that these gas separators create. So again, with the
The conventional separator, perforated sub, gas is produced, liquid is pulled in, gas escapes, and we're looking for the area between the perforated sub and the tubing and that dip tube, because that will give us a certain area, and we're concerned about how much area we're creating. So I think of it like a donut. We're trying to calculate the donut area between the dip tube and the gas separator. So with a pour boy, it was small. With a collar size, essentially it's a thinner piece of metal, the same OD as a collar. So essentially we have a little bit bigger donut area. Another type of gas
separator is a packer style separator. So it's something that's been around for quite a while, the 1950s, where we produce fluid.
We set a
packer and produce
fluid through the tubing up an intake, and then the fluid will fall down. So we've created an artificial sump, just like the pour boy with gravity separation, and then gas will go up the annulus. So with this, we create a significantly larger donut area because we're no longer producing inside of tubing with a dip tube. We're producing on the annulus of the tubing in a larger hole. So that separation area is significantly more. And so throughout the years, there's been different types of packer separators that have been created with all the similar designs. We're creating an artificial sump for gas to escape up the annulus and fluid to fall down. So when we talk about
maximum capacity, we're looking for that volume, that donut area, times by 50 barrels a day, 50 barrels per square inch, will give us a certain maximum capacity. So if we walk through those separators, and these are
very conventional separators. So a pour boy is the perforated sub. It's very economic to make. 2 7/8 sub with a 2.4 ID, a 1.3 dip tube gives us an annular area of 3.3 inches squared times 50 barrels a day per square inch gives us 166 barrels of oil, barrels of fluid per day capacity, and that's maximum capacity. So that's air and water. Collar size, we have a little bit larger ID, the same dip tube. We have a larger annular area, 229 barrels of fluid per day of maximum capacity. Packer style, where we're separating out fluid in the annulus, let's say we put it in a 5.5 inch well bore with a 4.7 ID casing. The OD of the separator is 3 inches. Essentially, we have more than double the
collar size or pour boy at 10 square inches. So we have a maximum capacity of 543 barrels. So not saying one's better than another, they all have their place, but this is how we would calculate a capacity or quote maximum capacity, which is something we see in industry today. So those were all laboratory studies, and if we take it out to the field, what we can do, what we're looking at is a pump card. So we look at the top left. Essentially what we want to see, and this is simplifying it, is a square pump card. If it's not square, something's going on, and maybe our rods are rubbing, maybe we're getting gas entrained. So what we can do is a step rate test. So essentially if we're
stroking this well at
5 strokes per minute or 7 strokes per minute, and we get a non-square card, if we slow it down, the card should square out, and from that we can infer what a bubble rise velocity would be. So if we've slowed our pump stroke down, we're pulling down fluid slower, so more gas should be able to escape. So I'm assuming everybody's shaking their heads because we're taking questions at the end, but that's basically how we would look at bubble rise and maximum separation capacity out in the field. So the second half of what I want to talk about today was solid separation. So pumps don't like solids. Solids grind. Solids wear things out. Solids cause erosion. And if we stop pumps, so like here in Oklahoma, we had a really bad winter snowstorm this year, and our wells were shut off for like a week. So essentially all those solids, sand, formation fines that were being produced up the well bore were
Basically shut down and fell to the bottom. And if they're in the tubing, they fall on top of the pump. And so if we have a stuck pump, we can have a rod part. It causes quite a bit of issue. So second part combined in production is solids. So what we see conventionally now is a hydrocyclonic separator. So hydrocyclonic separators been around since the 30s and 40s. And Dyson vacuum cleaners, wood mills. Essentially what it is that an inlet that spins solids. And the heavier the densities tend to go to the outside as they're spun. There's a cone that the solids hit and essentially fall out of the flow, and they fall downward, and the clean fluid goes up. So as work was getting slower during COVID, we started modeling essentially everything that was out there and see what would affect it, what wouldn't affect it, and started looking at. So this is a downhole hydrocyclonic sand separator. And what we see is this at a lower rate with the tolerances that are machined in these parts is that fluid can bypass it, and essentially the solids is still stuck in solution. So that's something that we want to avoid, is the cyclonic action needs to be enough where it spins those solids to the outside. And so if we size it right for the rates, we get enough velocity and we're able to move that solid out of solution. And so this slide is just showing there's multiple methods for fluid and solid separation. So there's a multi-spiral. So the cyclonic is essentially just spinning over a certain length before the intake. There's a disconnected spiral, but with the disconnected spiral, if the fluid rate isn't high enough, essentially the fluid will just go down the inside and bypass the spiral. So I think that kind of brings us to the conclusions is downhole gas and solid separation is an issue. We have separators out there.
We have gas and solid
separators out there that work various models, but I think it's important to know the differences between them and which method you would employ in a certain type of well. So they don't all work the same, and they don't all work in all applications. And that's essentially all I had. Any questions?
Thanks, DJ. That was interesting. Any questions for DJ? None?
DJ, I have a question. This is Duncan Brown. When you're doing some of that modeling on some of that, I guess, the sand efficiency kind of getting spun out of those, how are you actually using the concentration of sand in that, and how is that affecting your results?
We haven't played too much with the concentrations. We've changed sizes, but essentially with the modeling software we just have to put in a constant stream and then determine the size. And so it's all relative, essentially, is what we're looking for. Is, does this change make it look better, or does it make it look worse? And so what we've seen is in horizontal wells where they tend to slug, at certain points, they'll bring up more solids than one of those separators is able to handle. And so we've talked about different designs as far as a two-stage sand separator, but as far as being able to model like something like that, we just haven't been able to.
Okay, because yeah, that's basically what we've kind of seen before, is when we've looked at some of this stuff and working with people, is that you can run 100 mesh sand through it and it'll separate it out, and you can run 20 mesh sand through it and it'll separate it out fine. But when you have when you increase that concentration, it's really where you just overrun that separation capability, and end up with a lot of, I guess, stuck pumps in a short amount of time.
Yeah. Yeah. And so I think, I mean, the problems are seen all over the country. And I think we've tried experimenting with some two-stage. So having just a solid separator down below and then a gas and solid separator up above. I don't think we have long enough to say that it's working better or worse, but it would be a two-stage that may be able to help with that inconsistent production or solids production.
Adam, did you have a question?
So there's a question, did you develop any corrections to the max volume or bubble rise to account for different oil and gas viscosities? No, the rule of thumb is take those max capacities at 6 inches per second and cut it in half. And again, every area and every combination and even well is different. As far as your viscosities and gas, it's just, you can play with that, essentially slowing down your pumping unit to see if you can infer a rate. So if you slow that pumping unit down, you would tell what you're producing versus what you were at a different rate, and then you can maybe chart that out a little bit better. But no, I haven't seen a good rule of thumb or a good chart in certain fluid types, gas types.
Okay. Any other questions for DJ?